Welcome everyone, I am Uri, and we're going to take a stroll together down the security tools zoo. If you look at the world of security tools that help you find bugs in smart contracts before you deploy your code, we can see that there are many different technologies, and each of them has a very intimidating title that sounds very scientific and foreign to most people, like static analysis or formal verification, invariant testing. Seems like you need to have a PhD just to understand these terms. So today we're going to demystify them and explain what they actually do. And we'll briefly go over how they're implemented, but we'll only scratch the surface. What we will dwell on is how they're actually used in practice. What you should be mindful of, what you should try or not try to do, what are the limitations, and so on. And after we do that, we'll also learn how can we measure the effectiveness of our tool usage. And obviously, we'll also see some cute animals along the way. At first, we'll start by explaining what tests are. It's just to set up the discussion. Tests are the first line of defense that you have against bugs in your smart contract code. In this presentation, we'll take as an example a transfer function that gets 3 different parameters, 2 addresses and an amount. And that amount should be transferred from the first address to the second. So a test could look, for example, like this in Forge, written in Solidity. So here we have a test that we transfer 1 token from the address called Alice to an address called Bob. And then we check that Bob's new balance is equal to exactly 1 token. So one common theme among all tests is that they all check for a specific input, 2 specific addresses, Alice and Bob, and a specific amount of 1 token that we try to transfer. We're also checking for a specific scenario, a specific combination of specific functions. In this case, only the single function transfer. What people sometimes tend to miss is that tests usually only look at one specific starting state. What we usually do, say, in Forge is that we have a setup function where we tell it what are the 2 addresses that we are going to care about, and we're minting tokens, so we are actually setting a specific balance for the tokens for those addresses. So a test is a combination of very specific things. Examples for unit tests that you're probably pretty familiar with this is that we'll probably try to transfer 0 tokens, transfer the max UN 256 amount of tokens, transfer the entire balance of Alice to Bob, try to transfer to the 0 address, and so on. And if tests were an animal, they were a mole, because a mole is blind. A test checks only the specific thing it was set up to do. Tests are cheap to write, they're fast, and their largest advantage is that it's easy to understand relatively what went wrong when they fail. Because you wrote the test, hopefully you wrote some documentation of it, and you're looking at a very specific thing, so it's relatively easy to trace back and see what went wrong. And again, as we said, they have low coverage, specific starting state, input, and scenario. If we want to scale it up and check more inputs, then we should look into fuzzing. And there are several fuzzing tools in existence. One of them is Echidna by Trail of Bits, and there is Foundry, and there is a tool by Consensus Diligence, and there are many others. Fuzzing is the process of generating many different inputs automatically and testing all of them. When do we stop? So we allocate some limit to the computation. Usually it's either a limit on the amount of iterations, the amount of different inputs that we put, or just the amount of time. Try as many inputs as you can in 10 minutes. Obviously, the more resources we allocate to the fuzzing and we don't get an error, the greater will be our confidence that we don't have a bug in the function that we test. So obviously, there are some examples here on the screen. It's just inputs that may look completely random to a human. However, in practice, they rarely are truly random. Fuzzers are always smart to some degree. The inputs are not truly random. Fuzzers try to optimize for example, coverage. Many fuzzers will try to cover as many branches as possible in your code. Some fuzzers are even smarter than that and will check for some storage values in your contract and try to use them as different inputs, and so on and so forth. This is the difference between the different fuzzing products that there are. Some fuzzers are actually even smarter than that and can check a different type of test we call an invariant. An invariant is something that is always true about your system, even as it goes through transformations. And there are many invariants in DeFi. One of them you can see on the screen. This is a simple token invariant. We say that the total supply of the token is equal to the sum of the balances of all the different addresses, which should always be true. It doesn't matter which function we're calling. That's why it's an invariant. Another type of invariant you can think about is what we call solvency. And that could be, say, a property of a vault. And that's basically the opposite of what happened to the SVB bank. We always have enough assets to cover all our liabilities, and so on and so forth. And how fuzzers can actually check these invariants is that they call random functions, and usually a series of calls to random functions. But eventually, it's all the same thing under the hood. There is a theorem called the infinite monkey theorem. It says that if we'll give a monkey a typewriter and an infinite amount of time, the monkey will eventually type the entire works of William Shakespeare. And fuzzers kind of work the same way. It's sort of a brute force approach in which we're trying many, many different inputs in hope of finding that rare bug, which is like the works of William Shakespeare. So a fuzzer is a monkey. Fuzzers are cheap, and they're easy to set up. Usually, you can just reuse the tests that you already have set up before. We can see that with Foundry. And in practice, they are very good at catching some classes of bugs, which are relatively common, meaning that they occur on many different inputs. However, they still don't cover all the states or all the inputs or all the starting scenarios. It can only check some subset of them. Can we do better? I'll give you some motivation for it. MakerDAO have a stablecoin called a multi-collateral DAI. And quite recently, they have found out that something that they thought should always be true about their token is wrong. It was called the fundamental equation of DAI that should tell you what is the ratio between the depth and the amount of tokens that there are. I'm not even going to explain what that equation is. The interesting thing to see is that this is the minimal example to recreate this bug, right? So it's a combination of calling 8 different calls in a specific order with a specific relation between the different inputs. So obviously, you can put in between them some irrelevant calls, and the inputs are not specific, just the relationship. But the chances of us uncovering this with fuzzing are pretty low. So what can we do? If we'll go back to school for a moment, we have all learned the Pythagorean theorem. The Pythagorean theorem was proven to us, and we know that it's true for every right angle rectangle. And we know this without actually checking all the different rectangles in existence, which is basically what we were trying to do with fuzzing. And we were able to prove it using mathematical theorems. And this is essentially what we're going to do with the following technology called formal verification. Formal verification takes your code and transforms it to math, and then tries to prove that math equation. The downside is that if you transform your code into math, you should also transform your tests into math. And we call those math tests specification, or even formal specification, because it's as formal as a mathematical equation. There are different types of formal verification. The two that we're going to discuss are symbolic execution and theorem proving. First, let's look at an example for a specification. This example is written in the Certora verification language, which is the input language for formal verification tool by Certora. If we look at it, we see that it's actually not that different from the test that we saw earlier for the transfer function. So we check the balance of Bob before the transfer, we transfer some amount from Alice to Bob, and we check that the balance of Bob grew exactly by the amount that Alice has sent. What are the differences between this and the test that we saw before? Well, here we don't know what the balance of Bob was before the transfer. It's no longer necessarily 0. We also didn't set up the addresses of Alice and Bob, and more interestingly, we didn't set a specific amount. You can think of it like an X symbol in math, checking for every amount. The first type of formal verification that we will discuss is called symbolic execution. There are several tools on the market that do this. There is the Certora tool that we've discussed before, there is Manticore by Trail of Bits, and there is Mithril by Consensus Diligence, and others. The basic idea of symbolic execution is that we give the specification, which is the math test, and we give the code, and we get 1 out of 3 possible outcomes. Either we get a proof, which is a mathematical proof, that our code behaves as we've wanted to, as we've defined in our specification or our tests. And that's great. That gives us some confidence. Greater confidence than just trying some subset of inputs. Another possible outcome is a violation. And when we get a violation, we get a specific set of a starting state and inputs, which violates what we wrote in the specification. And this is an unexpected behavior, which oftentimes is a bug. The third option is that the tool cannot decide and just times out. Symbolic execution is a turtle. It gives us the maximal amount of protection. See, it covers so much. And again, the big difference between this method and the previous ones is that we have some mathematical proof for the absence of specific bugs. And I also want to mention that just the process of writing what we call the formal specification is oftentimes enough to uncover bugs in the design or the implementation just by itself. However, as a turtle, formal verification is slow. Formal verification, at its core, theoretically, tries to solve what we call an undecidable problem, which means in practice that first, we have to bound what we're trying to do. For example, we're not proving anything for an infinite amount of iterations in loops. What does it mean if, for example, we have a function that runs over an array with a variable length? We will limit it to, say, 3 iterations, 8 iterations, or some limit. What it also means is that it doesn't matter what, we will always have some programs and some specifications at which we will fail. Fail miserably, meaning we will time out, no matter how much time we're going to give. Formal verification will be as useless as a turtle flipped on its back. And this is unavoidable. It will sometimes happen. This is inherent to the technology. However, we see that in practice, this is not the limiting factor. The limiting factor is the need to write those math tests, those specifications, which is hard to do. It's not natural for many programmers. And there is a problem of what happens when the specification is not good enough. If the specification doesn't actually mean what you wanted to prove, or there are some key properties of your code missing from the specification, then it's not going to cover you from bugs. It's the same as tests. If you didn't write the test that can catch the bug, you will not see it. And formal verification is exactly the same in this regard. There is a different technique to formal verification called theorem proving. It's mostly used by runtime verification with the K framework. I'm not going to delve into all the details, as this one is a bit more complicated, but the basic idea is that they use an even higher abstraction. We have a model, a mathematical model of the EVM, and it's already written. You don't need to write it again. What you do, you check the specification against a combination of the code and that EVM model. So two different mathematical entities, and what K is trying to do is to prove that they are actually the same, what we say they are equivalent in math. And this is a very hard problem, so sometimes the prover will need some help, will need some hints from the user, hence why it's interactive. There will be some problems that it will say, I don't know if it's true or not, and the user will need to provide some extra information. So that means that we have three different outcomes, but not the same ones as the ones we get in symbolic execution. One is a proof, and that's actually the same. If we have a proof, then we're happy. There are no bugs in the code, at least like in this specific instance that we've checked. We can also get a violation. However, that violation doesn't come with a counterexample. And now if we time out, it basically just means that we need to give another hint. If we do this enough times, we will eventually should be able to prove almost anything. So to sum it up, theorem proving is like an elephant. It can carry great weights. In practice, it was used to prove very complex systems, much more complex than smart contracts. It was used to prove airplane software or submarine software. And it's also unbounded. Like I said before, we don't need to limit the number of loops or any other things like that. However, it takes a while to tame an elephant, and that's somewhat true too for theorem proving. You need some expertise to know which hints to give to the prover, which is not trivial at all. And there is low explainability, meaning again, you don't have that counterexample, so if the proof fails, you need to try and figure out on your own what went wrong and how, and that's not easy. So we see that writing specifications is a drag. It's not easy, it's hard, it takes time, it costs money. Can we enjoy some of the benefits without writing specifications? So one thing that basically all formal verification provers come out of the box with is the ability to check that some bad reverts in your code don't happen. This could be reverts due to assertions in the code, division by zero, index out of bounds, and all kinds of other things, which is nice, but very, very limited. And that's where static analysis comes in. And there are several static analysis tools in the market. There is Slither by Trail of Bits, and there are tools by Veridice and Consensus Diligence. Static analysis is the process of looking at your code and examining it without running it, hence why it's static. And how it's done, static analysis tools have a set of detectors that are looking for specific predefined bugs in your code. What does it mean? Let's look at this example. This was taken from Veridice's website. So we can see that they check for reentrancy, or check for access to uninitialized state variables, and so on and so forth. There is a list. However, while we're trying to have a one-size-fits-all tool, we know that in some design patterns we actually use reentrancy, and sometimes we actually do access uninitialized variables in order to, for example, save gas. So not necessarily the things that static analysis will complain about will be actual bugs in your code. Static analysis is like a goldfish. It's cheap and it's easy to maintain. Usually You just plug and play, give it as an input your source code, and it will tell you all the problems that its detectors may find. It's also very pretty. It tells you exactly what was the thing it was designed to find, and will explain to you the attack, show you previous exploits, and you can have loads of documentation on every detector. Pretty like a goldfish. However, like a goldfish, it's confined to its aquarium, meaning it will never be able to find a bug that it was not programmed to. If there is no detector for something, then the static analysis tool will never find it. And also, from a practical point of view, these false alarms are a real problem. There are plenty of fish in the sea. This, for example, is me running Slither on one of the simple smart contract codes we use in Certora for testing, and there are several pages worth of warnings or alarms. In this specific case, none of them are actually relevant or interesting. None of them are a real bug. So what you gain in simplicity of use, you somewhat lose in that you need to spend some time in weeding out those counterexamples. To sum this part of the presentation up, in practice, each company uses a combination of technologies. It's not a single animal, it's a hybrid animal. Certora uses static analysis to improve formal verification, Consensus uses static analysis to improve fuzzing, and Veritas uses fuzzing to improve static analysis. And there are many more examples, so keep that in mind. Okay, so we've seen all the different animals, and now it's time for zookeeping. How do we know that we treat these animals right? How do we know that we are using our tools effectively to find bugs? One way is to have a human inspect them, meaning you have a person, an engineer, look at your tests, at your formal specifications, and so on, and check if there is something missing, if there is something wrong. Another option is that many tools will report what is the code coverage that they have. And you're probably familiar with this from testing, also from traditional software. We have different types of coverage, branch coverage, and line coverage, and many, many others. However, there is another type which is somewhat less known, which is called mutation testing. And the idea is that we're trying to test our tests. We take the source code and introduce some random faults in it. The code with a random fault is a mutant. And we expect that mutant to fail at least one tool or one test in our test suite. I'll show an example. This is a code of the transfer function that we saw before. It contains no bugs. And therefore, it should pass all our tests. However, we've created a random mutant of it. In this example, we can see that the first line has been omitted, has been commented out. Okay? And we expect that this wrong function that doesn't make any sense should fail our tests. And if the mutant is not failing any of our tests, then we know we have a problem. We know we have missed something. We have missed something in the test, in the specification, or something like that. Certora has a mutation testing tool called Gambit, and it's actually open source. You can go and use it with whichever other tool you want. What are the takeaways from this talk? Different tools, different technologies are like different animals. They behave differently, they have different limitations, different strengths, different restrictions, and different costs. We can see that there is no tool that is strictly better than the others. Each tool has its own disadvantages and costs. And the key to security is to try and combine several different technologies to cover the drawbacks of each other and find as many bugs as possible to secure our code.